so a economy based on hydrogen will be green. This is another thing that's very important, particularly in a country like that, where you have 1.2 billion people. You want to make sure that the fuel you use, anything that you do is green and economical, because there's so many people using these resources. The reason why it's green, because you could obtain hydrogen from electrolysis of hydrogen from water. This is actually not too new technology. It's been known for a long time, right? And the politicians are finally figuring out what electrolysis is all about, that's all. But more importantly, you could, in principle, obtain hydrogen from sunlight by using water splitting. Nature does this very well, right? And we can learn from nature again. And there's a lot of big push in America and elsewhere too, all right, to obtain hydrogen from water splitting. And of course, we all know for a long time already that there's a hydrogen-oxygen fuel cell that you could provide electricity. That's nothing new either, but we could make it better. That's the point. So some things are new here, but some things you could improve, and that's important. Photo splitting of water, that's one of the big push, all right? The photolysis of water to produce oxygen and hydrogen. It's been thought that this is the way out of the fossil fuel crisis by 2050. Now, as you know, in the United States, there's this couple of shale gas, shale oil, and the pressure, all right, to do this has gone down significantly from the fact that the gasoline has dropped from $5 or $6 a gallon now to 2.5 dollars a gallon, right? But this is a very political issue, right? We should not let that, right, decide how we should worry about energy in the future. Now, water splitting, be careful with what I'm doing here, is to take water and apply sunlight and in some way convert it to oxygen and water. That's what people mean by photosplitting of water. And of course, to produce a molecule of oxygen and water, you require removing 4 electrons, right? And generate 4 electrons. And the 4 electrons could go into protons to make hydrogen. That's the way people are thinking about the problem. But you remember in the previous slide where I show a photon, it takes a photon of a certain energy to do this, because it's not so easy to carry out this process, all right, with one single photon. But nature does it, all right, differently, all right. So the way people have been thinking about is use solar energy, all right. But in order to do what I just said, you need photons which are, shorter than this 300 nanometers. But most of the photons you see on the surface of the Earth is not that, it's much longer wavelength than that, right? And so you have to develop catalysts, all right, that will produce oxygen and water, hydrogen, all right, the photooxidation of water, all right, so that you could use sunlight efficiently, so that we cannot really, all right, do it directly. Now, in bacteria and plants, photosynthesis, the photons are absorbed by chlorophyll, right, of this particular energy. And the electrons are transferred from water, 1 electron at a time. Don't forget, 1 electron at a time, not 4 electrons at a time, right, to other low potential electron acceptors. Not protons directly, but something like protons to make hydrogen, or some molecule will accept electrons and make reducing molecules. The overall reaction of electron transport from oxidizing the water to the electrons and eventually to the molecule to pick up electrons is about 114 kilocalories per mole of oxygen, or 1.23 electron volts, okay, transfer. So there is enough energy to do this, even with 1 electron at a time. This is a crystal structure of cyanobacteria, the Photosystem II. And this is the membrane protein. I won't go into that in great detail, but that merely show you with the chlorophyll molecules embedded in the polypeptide, and to show at the same time there's a water cluster, manganese cluster, right, that will participate in the water oxidation. This is something called, right, the manganese water cluster, OEC, oxygen evolution complex. And what happens is that there's a reaction center, a parachlorophyll, that absorbs the sunlight, all right, in the wavelength that you normally could do that on the surface of the planet, and generate a hole. The electrons go through, all right, accessory chlorophyll and the pheophytin, and eventually it gets transferred to a quinone, right, to make quinol. That's how the electrons are stored, not directly into hydrogen, but in a molecule which is reduced, and then in principle you could take the hydrogen out indirectly, all right, later. Water is oxidized to produce oxygen at the oxygen evolution complex. So this hole, all right, that is generated by photolysis and forces the electron to leave the reaction center, gets replenished, right, by oxidation of, all right, water to form oxygen, one electron at a time. So after 4 photons, all right, you get an oxygen molecule produced. The free energy that I talk about, 114 kilogram per mole, is an overall reaction, all right, from a water molecule here, all right, to all right, hydrogen stored in the quinone. So here is another picture of this structure. Here they show it basically remove the polypeptide and leave only the skeleton. There is a special paired reaction center, a pair of chlorophyll molecules that absorbs the light, all right, and it gets excited, all right, into, all right, a LUMO, the lowest unoccupied molecular orbital. The electrons leave there to go through this accessory chlorophyll in the pheophytin, and then it goes to a reduce a quinone to a semiquinone, and then to a quinol. Here's the iron center that helps this process. So this is I basically took out the part that's important for the oxidation of the reduction of the quinone. All right. So in the photosystem, the algae and green plants, the reducing equivalents of water oxidation actually is transferred to a quinone molecule. All right. And so this is the overall reaction that's what I'm talking about. All right. And you need 4 photons, all right, to do this. And here I show it again a different way. in purple membrane, the reaction special pair accepts a photon at 960 nanometers. All right, and here's a bacterial pheophytin, and it transfers the electron, right, very fast actually, in picoseconds. And then it transfers to this quinone to reduce the semiquinone, and then very fast. And eventually, after 2 electrons, it reduces a quinone molecule to a quinol. And this quinol molecule then donates its electrons to cytochrome BC1 in the purple membrane. And then, of course, the rest of it is not so important. Right. Okay, so this is purple membrane. This system does not do water oxidation, but in green plants, it has something similar, except that there is an oxygen evolution complex that will actually pick the electrons, uses this reaction oxidation, right, to pick the electrons away from, all right, from water molecules, and after 4 electrons, we'll make an oxygen molecule in the process, all right, like 1 electron at a time. After every chemical event, will transfer the electrons down to a plastic quinone to make the plastic quinone. And here, all right, the reducer equivalent is stored. Nature does not make hydrogen in this process. Don't forget, that's my point. All right, and this is very important later on because it's much better to store equivalents of hydrogen in a molecule than to store it in a tank. right? So because it's not safe in a tank. Okay. There are bottlenecks in the hydrogen economy, of course. Storage of hydrogen under high pressures. There's a technology. I mean, there have been many ways. People have thought of many ways of storing hydrogen, all right, at low temperatures, using palladium, many noble metals. Obviously, that's not practical. Hydrogen under high pressure poses a serious environmental safety issue as well. You need efficient and durable catalysts for water splitting by sunlight. We're still working on that in the laboratory. We still don't have a way to do this. Right? Nature does it very well, and we begin to understand how a plant actually carries out this process. In the hydrogen oxygen fuel cell, you need a replacement for platinum. It's not practical, right? To do this hydrogen oxygen fuel cell with platinum. There's just not enough platinum around. It's very expensive. Right? We need another, non-precious metal that's cheaper and more abundant to redo this chemistry. This is an unsolved problem, even though people are actually inching towards a solution. And something that people don't talk about, clean water, which is needed for water oxidation, is not a cheap commodity. We're slowly running out of really cheap water. Any impurities in the water that's will poison the electrons, and this is a practical problem. Okay, in the short foreseeable future, a methanol economy may be more practical and realistic than hydrogen economy. And at the end, I will tell you that a technology or economy based on the use of methanol and hydrogen indirectly is a viable source to some of our problems in energy. So what is a methanol economy? The methanol economy actually was first proposed by George Olah, a Nobel laureate. He suggested a future economy in which hydrogen replaces fossil fuel as a means of energy storage, ground transportation, the raw material for synthetic hydrocarbons and their products is important. Now, most of us think of methanol, hydrogen as a replacement for fossil fuel and for energy storage and ground transportation. But unless you're a chemist, you won't appreciate how important it is, how much we rely on fossil fuel for synthetic hydrocarbons and the precursors of the chemical industry. We take it for granted. The shirt, the jacket, many things. Plastic wouldn't happen without actually fossil fuel, and we need to find a way out, to generate the precursor molecules to do that, right? And as you can see, George Olah, was offering an alternative to the proposed hydrogen economy or even ethanol economy. Methanol, for those of you who are not familiar with chemistry, is just liquid alcohol, 1 carbon, 4 hydrogens, and an oxygen. And you could create from methane, the main ingredient of natural gas. We still have lots of amount of natural gas. In fact, off the coast of Taiwan, the southern coast of Taiwan, in the bottom of the ocean, there's a lot of methane tap rates, which you could actually tap, to use as a source of to make methanol. And of course, in some countries like Qatar, they're sitting on top of gas. And they need to find something to do with the gas, and it's very important. Okay, so this is a front page of an article that I recently published with an Indian postdoc by the name of Abu. He actually